So in this section, we're just going to review all of the different tests for series that we have looked at so far, and give examples. So first off, of course, there's the geometric series. This one you should have memorized, absolutely. So this guy converges if the absolute value of r is less than 1 and diverges otherwise. And the geometric series is unique in that we actually have a formula for the sum. Okay, so the divergence test. If you can tell at a glance that the terms of the series are not tending towards 0, then the divergence test is applicable. So remember, if a series converges, then that means the terms of the series have to limit at 0. So if they're not limiting at 0, then it must diverge. That's all the divergence test says. So in this example, you can clearly see that the limit as n goes to infinity of this dude is going to be 1/2, because the degree on the top is 1, the degree on the bottom is 1, so the limit is the ratio of the leading terms. And yeah, you should be able to tell that just by looking at it, and immediately conclude that this dude diverges. So because this limit is not 0, this series converges. Or diverges, rather. Okay, the integral test. This basically just says that if your function is continuous, positive, and decreasing, and you know how to find the antiderivative of it, then the behavior of the improper integral from whatever out to infinity is the same as the behavior of the series. So the integral test is going to be useful when the terms of the series look like something that can be anti-differentiated. So in this case, here we have x e to the minus x squared. This is an integral that we've done before. In particular, this is an integral that can be achieved by letting u equal x squared. Yeah, and it's not too hard to see that it's positive and decreasing as well. But yeah, let's just go ahead and do the integral. Like so. Yeah, so the point is we can anti-differentiate this guy by letting u equal x squared. Because then du is equal to 2x dx, so that means that this x here is going to get canceled out when we plug in the dx. We should also be careful to accommodate the bounds. So when x is equal to 1, u is equal to 1 squared, which is also 1. When x is equal to infinity, or rather in the limit as x goes to infinity, u is x squared. Okay, so that's also infinity. So the bounds actually don't change. So x squared becomes u. Dx transforms into 1 over 2x du, and these x's cancel, which is what we expected. So we have a 1/2 that we can pull out. And we just have e to the minus u, du left over. So we can anti-differentiate that because that just becomes minus e to the minus u. Evaluated between 1 and infinity. So that minus 1/2 we can pull out. When we put in infinity, well, we get that. When we plug in 1, we get that. So what is the limit as x goes to negative infinity of the exponential function? Well, that's 0. So this becomes 0, minuses cancel, so we have just 1 over 2e to the negative 1. Okay, well that's the same as e over 2. So the point is, the improper integral converges. So the series converges as well. Okay, p-series, I mean, that's easy. P-series are usually going to be the things that we're comparing to when we do one of the comparison tests. Speaking of the comparison test, we have the direct and limit comparison tests. The direct comparison test is rarely ever useful, but if you have something which is very, very similar to a geometric series or very, very similar to a p-series, then the direct comparison test might be useful. So for example here, this is, if that 2 wasn't there, if this was just 1 over 3 to the n, that would be geometric, with r equal to 1/3. So this guy is very, very similar to a geometric series. When r is really big, then this 2 can be neglected, and so this dude is eventually going to look like a geometric series. So let's compare to the convergent geometric series 1 over 3 to the n. Why is this convergent? Well, because r is equal to 1/3, and the absolute value of 1/3 is smaller than 1, so, right? If you have a geometric series where the r is smaller than 1 in absolute value, that guy's going to converge. So we want to make some sort of inequality. So start with an obvious fact. So clearly 2 plus 3 to the n is larger than 3 to the n. Now 2 plus 3 to the n is in the denominator, so that means we have to reciprocate. And reciprocating is going to flip the inequality. Okay, so the larger series converges, that means the smaller series has to converge as well. The smaller series, of course, being the one that we are interested in. Now, the direct comparison test is occasionally useful, but really the limit comparison test is where it's at. That one is much more broadly useful. And in particular, it's useful whenever the terms of the series are given by algebraic functions. So an algebraic function is something ugly like this, where it's got polynomials and square roots. So in this case, we can find a series to compare it to just by taking the leading terms and ignoring all the other terms. Right? Because when n is large, only the dominant terms are the ones that are well, that'll be dominant. Those will be the only ones that matter. So we find that when n is large, this dude is approximately, well, we can neglect the plus 1, so that's just n to the 3/2 on top. The cube is the dominant term, so we can neglect the square, we can neglect the 2. So 3n cubed. And then we can simplify this because 3 minus 3 halves is 3 halves again. Now, this is a p-series where p equals 3 halves is larger than 1, so the series that has this as its terms is going to converge. And that 3 doesn't matter, you can just factor that out. Right? P-series, if p is larger than 1, then it converges. Okay, so if we do the limit comparison test, we take the limit of the ratios of the two series, the one that you've been given and the one that you're comparing it to. And then if this limit is a finite non-zero number, then these two series have the same behavior. In particular, since this guy converges, the one that we're interested in would also have to converge. So let's see. So on the top, let's put the terms of the given series. On the bottom, let's put the guy that we are comparing it to. Okay, and now we need to figure out what this limit is. So first off, of course, if you're dividing fractions, that's the same as multiplying by reciprocals. So definitely want to get that out of the way first. Like so. Okay, so what is going on here? Well, this square root is a little bit vexing, so let's make it so that everything is underneath one big square root. So on the top, we have, well, let's see, n cubed plus 1. Here, 3 is the same as square root 9, and n to the 3 halves, that's the same as square root n cubed. On the bottom, this is the same as the square root of all of this junk squared. Like so. And now, because the square root is continuous, I can pull this limit inside. Okay. So now this limit should be easy because this is just a rational function. We have a polynomial on top and a polynomial on the bottom. Now, to be fair, squaring out the denominator, foiling it, is going to be a real pain, but you don't actually have to get the whole thing. We only care about the degree. So to get the degree, we really only need the leading term, which is going to be what we get when we take the 3n cubed and square that. So since So what's the leading term on the top? Well, that's going to be 9n cubed times n cubed. So that's 9n to the 6 plus, who cares? I mean, it's just 9n cubed, but I'm trying to make a point here. On the bottom, we only need the leading term, so that's going to be 3n cubed squared, and then there's going to be a whole bunch of other junk, but that other junk is all going to be smaller. The degree is the exponents of all of the other terms are guaranteed to be smaller than the degree of this first dude squared. So that would be 9n to the 6 again. Okay, so the degree on the top is 6, the degree on the bottom is 6. That means we only need to take the ratio of the leading coefficients. That's 9 over 9, which is 1. So the whole dude is just the square root of 1, which is 1. Okay, so we are doing the limit comparison test. We got that the limit is 1. That is a finite number, and it is non-zero. So that means the series we have and the series we're comparing it to have the same behavior. In particular, because this guy is a convergent p-series, they both converge. Okay. Alternating series test. So again, it's pretty obvious when this one is going to be useful. It's when you have an alternating series. However, I should note that there are a couple cases in which you have an alternating series where a different test is actually going to be more convenient. Because, for instance, it's possible to have a geometric series where r is negative. Because if r is negative, then it's going to end up being alternating. But it's geometric, which means that, you should use the facts about geometric series to evaluate it. Similarly, if the terms of the sum contain factorials or some combination of exponentials and polynomials, then even if it's alternating, the ratio test is still going to be more useful, because the absolute values here are going to kill the alternator. So the ratio test can also be useful for alternating series. So that really just means that the alternating series test as written is most useful when you have an alternating algebraic series. So when you have an alternator and the remaining terms are, it's some sort of algebraic function. Again, like something like this, that has roots and polynomials in it, which is exactly what we're looking at here. Okay, so let's verify that the premises of the alternating series test are met. Are these dudes positive? So let's see. Here we have b sub n is n cubed over n to the fourth plus 1. So clearly these are positive. For positive n. Right, if n is negative, then the numerator might be negative, but, we're starting at n equals 1, and it's only getting bigger from there, so that's nothing to worry about. Is the limit going to 0? Well, we have a rational function, so we only need to compare the degrees. In this case, the degree of the numerator is 3, the degree of the denominator is 4, so that means the denominator is dominant, and that pulls the whole thing down to 0, as desired. And finally, is this guy eventually decreasing? Well, it's not immediately obvious to me that this guy is decreasing, so we should take the derivative and show that the derivative is negative. Okay, so we're doing the quotient rule. So low and I changed n to x just because taking derivatives with n's makes me nervous. So low d high minus high d low over low squared. So the denominator is a square, so that's always going to be positive. So we really only need to show that the numerator is negative, or that the numerator is eventually negative. So let's see. Distributing, we get 3x to the 6 plus 3x squared minus 4x to the 6 3x to the 6 minus 4x to the 6, so that's minus 1x to the 6, and we still have that 3x squared there. Okay, so in the numerator, the x to the 6 term is clearly dominant, so that means that when x is large, the negative x to the 6 is going to control the sign of the numerator. So indeed, when x is large, the numerator is going to be negative. So negative over a positive number is all negative. Okay, so that's all the premises of the alternating series test. So we conclude that this dude is convergent. So we conclude that's convergent. Okay, so finally we have the ratio and root tests to look at. So, like I was saying earlier, the ratio test is really the most useful if you're looking at a series that contains factorials, or if it contains some combination of exponentials and polynomials. So in this example here, we've got a factorial, so automatically that tells me that ratio test is going to be the thing to use. Also, the reason that the ratio test is so effective with factorials is because of the following property of factorials. So n factorial is equal to n times n minus 1 factorial. It's this property that's going to allow us to do a whole bunch of cancellation. Okay, so in the ratio test, we have to compute this limit, and then that will tell us everything we need to know. So we take the n plus 1th term, over the nth term, and of course, dividing fractions is the same as multiplying by their reciprocals. Whoops, reciprocals. There we go. Now in this case, everything is clearly positive, so the absolute values don't really have anything to do. So let me rewrite this so that the like terms are on top of each other. So n factorial over n plus 1 factorial, and 2 to the n plus 1 over 2 to the n. Okay, so now we can start doing a bunch of cancellation. So first off, this n plus 1 factorial, so using this fact, this is the same as n plus 1 times n factorial. Over here, this is the same as 2 to the n times 2 over 2 to the n. So the n factorials cancel, the 2 to the n's cancel. So we are left with 2 over n plus 1. Okay, so what happens to this dude as n goes to infinity? Well, we just get 2 over infinity, which is 0. So what's the conclusion? The limit is 0, which is smaller than 1, so that means this series is absolutely convergent. Okay, finally we have the root test. And the root test is really only useful if taking this big nth root is going to simplify the stuff that we've been given. So examples where you use the root test are all kind of contrived, but you'll notice that they always have like this big ugly power of n everywhere, because, you know, that's just setting up for this nth root to simplify things. So in particular, so we compute this limit. Okay. So everything is positive, so the absolute values don't really have anything to do here. So that means we can just go ahead and take this 1 over n and apply it to the top and the bottom. So that's going to divide out this n and divide out this n. So this is n squared over 1 plus n cubed. Okay, so now we just have a rational function. So all we need to do is compare the leading terms. So on the bottom, cubing this whole thing is going to be tedious, so we really only want the leading term. So that's going to be n cubed, and then a whole bunch of other junk. So the degree of the top is 2, the degree of the bottom is 3. That means the bottom is the dominant term, and it pulls the whole thing down to 0. And then the conclusion is the same. Since L is smaller than 1, we conclude that the series is absolutely convergent. Okay, so that's it for this one. Really just a review more than anything else, and to sort of contrast the use cases of all of the different tests that we have. It's a lot of different tests, but you know, they all have their uses. So yeah, when you're just looking at a series and you have no idea of what to do with it, just compare it to one of the examples here, and maybe that'll give you an idea of which test is going to be appropriate for it. Okay, so that's all for this one.